Okay, welcome back to video 3 of week 2 of Physics 325 Optics. In the last video, we talked about this paraxial approximation and how we can treat this complicated multidimensional wave as a ray, as a line. And that opens the door to something called ray optics. Previously, we had worked with light as an electromagnetic wave, that is electromagnetic optics. There's even a third picture that I've alluded to a few times, which is photon optics or quantum optics. Now it turns out that each of these kind of nests like Russian dolls into layers of into regions of validity. And we're going to kind of reconcile this picture today. We're going to talk about the three pictures of optics. So last time with this paraxial approximation, we talked about ray optics. What is ray optics? Well, where is it valid? Well, it's valid whenever the diameters and kind of sizes of the apertures or things that the light is bumping into is much larger than the wavelength. Conversely, we can say that we can take the optics and the limit as the wavelength goes to 0, then things behave more and more like pencil-like rays. As soon as that's not true, as soon as you have wavelengths that vary, the wavelength of light varies, for example, over the width of a slit or something like that, that can lead to very different behavior that we can't predict from ray optics, from these pencils of light, and that the theory breaks down. We have to go to electromagnetic waves. Okay, so what are the postulates of ray optics? Well, we just said that light is made of rays. Now we don't know what those rays are. What are the rays made out of? It kind of just kind of delays that question. But light is made out of rays, and they travel in straight lines at the speed of light. More on that on a second. So they reflect and they refract, and they can transmit through things. And they obey laws like the law of reflection and Snell's law, which we're going to derive more generally next week, actually. Okay, so it turns out that when it goes into a medium, it travels slower than it would in free space. The ratio of the speed of light in free space to the speed in the medium is known as the index of refraction. So it moves at velocity c over n, which is the index of refraction in that medium. And this is the picture of optics that many of you may have seen in previous courses. Okay. So I said that they travel in straight lines at the speed of light. Well, that's not totally true. It travels at a reduced speed, generally in matter. But also, why does it travel in straight lines? It turns out it doesn't always travel in straight lines. We will talk about this a bit later. It can travel in curved paths if the index of refraction is continuously changing. Also, we might have seen that if you shine a laser into a fish tank or something like that, being careful not to shine it in the fish's eyes, the light will bend at that interface. So it's not always in a straight line. What it does is that it travels in such a way that a quantity is minimum. And that quantity is known as the optical path length. Basically, we just integrate all possible indices of refraction, the index of refraction over all space, and the light is going to travel in a path that minimizes that. It seems like magic. How does it know? Now, this is a potential topic that we could talk about in the last week if you want to vote for it. This is completely explained in quantum electrodynamics. In fact, this book, Richard Feynman's QED, kind of shows some very nice pictures of why that actually has to be and why that makes sense. It's a very readable book. I recommend it. So this is the picture of ray optics. But we got ahead of ourselves a bit talking about QED, because let's go to the next step, the more general case of optics, when we have things like the single slit or the double slit, and we get weird things that we scratch our head over that we cannot explain with rays. Well, we go to the next stage, which is electromagnetic optics, and we've seen this already so far. The postulates of electromagnetic optics maybe make a bit more sense. We don't say that light is made out of rays and those are made out of whatever. Light is a wave supported by this medium called the electromagnetic field. So there's an electric and a magnetic field permeating all of space. And if I flick it, or if I take a charge and I wiggle it, I accelerate that charge, that causes a ripple through this electromagnetic field, and that ripple as it propagates out is what light is. And what's nice about this picture is it actually explains some of the physical mechanisms between reflection and refraction. We can actually understand why that has to be the case. We just need to look at what happens to matter as it is oscillated and pushed around by electric and magnetic fields. We're going to do that next week. We're going to find out that if we just look at the light hitting an interface right before versus right after an interface, there's going to be a relation such that we can completely reconstruct the laws of reflection, refraction. We can even find out how much light is bouncing off and how much goes through. All right, so we really get a good physical picture. And in fact, this is a very general theory. It's more general than ray optics. It's the most correct classical theory we have. So we can use it to derive ray optics. So ray optics is a subset of electromagnetic optics. Typically, it's harder to do though. Ray optics is much simpler. We can draw quick diagrams to understand what happens to an image or what happens in an optical instrument. So how we're going to do things generally in this course is we're going to derive the physical mechanisms behind things. We're going to understand things at a deep level using electromagnetic optics. And after we've derived it, we'll put it in a box and we'll just use the results from it to see what happens to the rays and have a much simpler picture. All right. There's a word about electromagnetic radiation. This can happen at different frequencies. So remember I said that if I wiggle that electric field, I happen to have a magnet here, I'm actually getting ripples in this electromagnetic field which are propagating outward at the speed of light. Now I can do this at about, I don't know, a few hertz. If I could do it at 1,000 hertz, like so fast that it would be, there'd be probably a hospital visit to my arm. If I could do it that fast at 1,000 hertz, we'd still not be anywhere near the light that we see. In fact, the wavelength of that, because we have this relation, the wavelength times the frequency is equal to the speed of light. Because the speed of light is so fast, if I'm only wiggling it 1,000 times per second, the wavelength is very, very, very long. 10 to the 5 it looks like, so 100 kilometers or so. So 10,000 times per second we have these 10 kilometer waves. We call those very long radio waves. And there's some stellar sources that emit those long radio waves that we can detect. If I wiggled the charge much, much, much faster, so that it's going 1,000,000 times or 10 million or 100 million times a second, we'd still be at radio waves. That's how fast things have to actually oscillate and accelerate to create measurable radiation. But eventually, if I start wiggling it faster and faster, we'd enter into what we call, as humans, microwaves. There's nothing fundamentally different between radio waves and microwaves. It's just a different number. So when we get into there, that microwave region, the waves start behaving differently with matter, right? When they're wiggling that fast, we can actually get more absorption. And that's evidenced by your microwave oven, which can actually heat things up. All right, so that is on the order of gigahertz. All right, so that's 10 to the 9, 10 to the 10 seconds for, 10 to the hertz per second. So it's still very, very, very fast, but these are long wavelengths on the order of meters or centimeters. Microwaves usually centimeters. I could wiggle faster and faster and faster and go to a terahertz or so, and 10 terahertz. And then I'm in what's called the infrared. I still couldn't see anything if I'm looking at this blur of a hand wiggling a charge, except for a blurry hand. And what you'd actually find, though, is that all of a sudden, if you looked at on a CCD camera, for example, it would start shining up. Because so some detectors could actually detect this radiation. It's the wavelength that's emitted by the thermal jostlings of an object that's hot. When they're starting to glow, before they glow red hot, they're emitting these infrared waves. And that's on the order of anywhere from just over a micron to tens of microns. We're into the infrared range. Now imagine we're wiggling that charge, and if I had sweet editing skills for videos, I'd actually make this happen. You'd actually start to see a faint red glow. And as I wiggle it faster and faster and faster, that it would become a much brighter red glow. And you're like, oh, it's just getting really hot. But no, it would turn yellow, and then as I was wiggling it faster, it would go green and then blue. I'd be into the optical range of electromagnetic frequencies. Okay, so that's on the order of 400 to about 800 nanometers of wavelength, and on the order of about 100 terahertz to 1,000 terahertz. That's the frequencies of these electromagnetic waves that we can actually see. I wiggle my hand even faster, and the light would disappear. It would still be there, but I'd get a suntan or a sunburn if I was doing it. I wouldn't be able to see it because we'd be into the ultraviolet range, the UV range. Okay, and that's somewhere between tens of nanometers to a couple hundred nanometers. All right. I could go even more. I could wiggle it faster to the point where the wavelength was on the order of a nanometer. And this is the X-ray range. X-rays have very, very short wavelengths. They're very good approximations to a ray of light, right? That limit of X is going down to 0. And that means they can kind of go through things without diffracting and get a good picture. So that's why you get X-rays to examine bones in your body. It's not the end. We have one more region to go, as I'm wiggling so fast that even flicking an atom with its electron charge around it, that cannot wiggle fast enough for this next set of waves, we have to bust apart a nucleus. And when we do that, there's so much energy and so much kind of jostling that emits extremely fast radiation known as gamma rays. And these gamma rays are from high energy particles or nuclear reactions, and that has extremely short wavelengths, 10 to the 12 meters or less. Okay, so that's the whole electromagnetic spectrum. So finally, this is all that we know from electromagnetic optics, and it turns out that there is some things that we cannot predict. If I look at the amount of light hitting the screen at a very, very, very fast time scale, light appears to actually be hitting small regions. Even though I'm illuminating it, there's little tiny flecks which are being lighted up one by one. And that is actually happening in these discrete bundles. So it's almost like light is transporting little bundles of energy that I cannot explain classically. So in order to do that, we have to take into account quantum mechanics. And this is the third picture of optics, quantum optics. Now it's the most general theory so far. It's given by QED, quantum electrodynamics, and it explains kind of everything. We can use it to derive electromagnetic theory, which we can use to derive waves. So it's the most general theory. There is only one or two effects that we need to go beyond QED. I think we need electroweak theory to talk about the polarization of outer space or something like that. But these are all crazy theories. This is the most general theory of optics that we really have to work with. And in this case, light, it's not that the electromagnetic field is a thing that's wiggling. In this picture, it's the wave function that is actually oscillating here. And elements of this function are what we call photons. They're an element of this Hilbert space. So it turns out that how fast those electromagnetic waves are wiggling, like we had before, that speed that they're wiggling at, that's proportional to the energy of the individual photon. So gamma rays have incredibly high energy. Radio photons have like no energy, and they're very delocalized. So this is the picture. So it's generally a very difficult thing to work with quantum electrodynamics. And it would be crazy to try to do things like the thin lens equation with QED. You can do it. I think people have done it, but it's highly unpleasant, and I wouldn't recommend doing it. I've never tried to do something like imaging with QED. But we can work in a picture as long as we have around the same energy of our detectors that we can detect individual photons. A nice simple picture emerges. So we're going to forget about all the quantum field theory stuff. You can study that in graduate school if you'd like. We're going to talk about a picture of photons, of light, sorry, is consisting of these individual photons. So what is a photon? That's actually a very contentious question. There's papers called anti-photon, and there's pro-photon papers, and people, serious physicists to this day are having debates on how much reality we should attribute to the physical reality that we should attribute to a photon. I did a PhD in photons, the photons that are emitted by atoms, and I still don't know what one is. In fact, one of the people that invented quantum optics, Roy Glauber, I think this is his quote, I couldn't verify it, so I'm sorry if I got it wrong, said something awesome that, I don't know what a photon is, but I know one when I see it. And that's basically what we're going to have to work with today. But we are going to use the fact that photons have a given energy, and we're going to treat them as massless particles. The fact that they're massless is very weird, okay? They have energy but no mass. Any minute force in classical physics means that they should go to infinite acceleration. And it means to us that they're basically moving at the speed of light. But if we try to combine that with reality, with relativity rather, and reality, it turns out you get some weird things. It should be, remember that the faster you are traveling to the speed of light, the slower the time, more time dilation you'd actually experience. So there's a very interesting question of the universe from a photon's point of view. So where is a photon? And we have to resort to one of these quotes by these snarky physicists that invented the theory. I think this one was by Myman. Don't quote me on that. Anyways, the quote is, what is a photon? Well, a photon is something that a photon detector detects. Where is a photon? It's where it gets detected. All right. And that's kind of the operational definition that we're going to work with in this course, because the photon itself is very delocalized. I'm very fascinated personally by this question. It's part of the stuff that I like to research. But for us, we're just going to look at photons as these little bundles of energy that are spread out, kind of delocalized through space, in such a way that they're going to get detected. When they are detected, they have a fixed energy at a fixed point. So here's a picture. This one's from Wikipedia, of a picture that's being developed. Unfortunately, when I dug into this, I saw that it was a simulation and I couldn't find a real picture, but you could do this. And for very, very low light levels, you're just going to see little blips of energy as the CCD from your camera is detecting a photon with some probability. And if we had a very, very short exposure time and we developed a photo from there, we just see a few little blips. Exposed for a bit longer, you start to see an image. And more of these black spots would get filled in as time goes on. Eventually you'd have a continuous image like you'd expect from a camera. But there's this granularity at the base of it all that implies the existence of these corpuscles or these particles of light. How about in time? They're actually spread out in time. And this is a picture from some of the stuff I was working on back in the olden days with my PhD. We're looking at photons that were emitted from atoms. And what we found is that you could actually map out the photon. We could look at the state of the electromagnetic field really at instances of time for many realizations of the same experiment. And they would form this probability distribution. Usually it's here, sometimes it's here, it's very seldom there. And what we found is we can actually look at the shape of a photon that's emitted from a process. So these things are spread out in space and they're spread out in time, but when they get measured at an instant in time at a point in space. And that's where we're going to leave it in terms of photons for understanding the true nature of a photon. But it's a really cool and fascinating subject. Now, there's something that just came out just this week, actually yesterday, I was reading this. A new paper came out where they're actually visualizing a pulse of light. Not a photon, but a bunch of photons in a very, very short pulse. Okay? So light travels very, very fast, the speed of light. It turns out when you look at that, the relation, it travels about a foot per nanosecond. A foot per nanosecond. So a nanosecond is about a foot of light. And if you have a sub-nanosecond pulse, it's about this, say half a nanosecond would be about this long of a pulse of light. So that's, if you have a very short pulse of light going through an experiment, it is like a little bundle of electromagnetic radiation. And this is an experiment where they actually visualized, they actually measured and saw a pulse of light going through an experiment. It's very cool. Let's check it out. You see that? So the light is pulsed on, it's going through the experiments, it's hitting some mirrors, and it hits that lens there. Isn't that amazing? We're actually looking at light. Let's look at that again. So it's pulsed. Look at the time scale there. This is in nanoseconds. It's bouncing around the mirrors, and we can actually see it propagate and go through the equipment, and reflect off things. That is a pulse of light being visualized. This paper came out a couple days ago. Very, very cool stuff. Okay, so that's what light looks like in ultra slow-mo. So I guess they had some scattering and then maybe a bit of fog in the lab, and they actually used a complicated machine learning algorithm because the data that they actually got was quite noisy. But this is what they got. They got the visualization of the optical field. All right. So let's talk a tiny bit more about photons. Another interesting fact is that photons have momentum. But what is momentum? MV? The momentum, as I remember it, is mass times velocity, and the mass is 0 for a photon. All right. So that's quite odd. It turns out that we can think about momentum differently when things are relativistic. So relativity, we all know, right? E equals mc squared. You've probably seen that one. E is equal to mc squared. Well, this is actually the rest mass. Okay? If things are moving, we modify that. So E squared is equal to mc squared squared, right? Plus the momentum, P times C squared, right? And this is the relativistic equation for energy. When things are moving, we have to add this extra momentum, this relativistic momentum here. So we just take this general formula and we cross out the mass, and we see that we do have an energy. E is equal to P times C, and that's equal to h bar omega, right? So E is equal to PC, and that's equal to h bar omega. So let's just write that out a bit. P, the momentum of a photon, is equal to h bar omega over C. All right, so let's write this out. This is h bar over C times omega. Well, what is omega again? Well, omega is equal to 2 pi f, which is equal to 2 pi, f is c over lambda, and that's equal to k times c. Oh yeah, omega equals ck. So let's go c times k, and these c's are going to cancel, and we have the momentum of a photon is h bar k. And it's a vector, so we'll put a little hat on it, is equal to h bar k. That's the momentum of a photon here. So it has momentum h bar k, and it has energy h bar omega. The fact that it has momentum is interesting. Imagine if I had a photon, and it's coming against here, I have h bar k of momentum, and it bounces off this somewhat shiny surface and comes back the other way. There's been a change of momentum. Before it was h bar k, now it's negative h bar k, so there's 2 h bar k worth of momentum. So if a photon is hitting a mirror, we've actually changed momentum, and momentum is conserved. So that mirror gets a bit of momentum, right? So that mirror is going to start gain a bit of momentum, which is h bar k worth, 2 h bar k worth of momentum. This is another way of looking at radiation pressure. And this recoil of momentum recoil of 2 h bar k is precisely what we measure in a lab when we look at an atom that's being bombarded by photons. Each photon, as it goes and it spontaneously emits, actually can move the atom. And that actually limits, it turns out, how much we can kind of trap and hold on to an atom when we're trying to do a technique known as laser trapping. Okay, that's it for quantum optics for now. That's it for photons. Let's summarize. There's 3 pictures of optics. Okay, there's ray optics, which is kind of the least general. Light consists of waves. No, ignore that. Light is consisting of rays, and it's valid in the limit that lambda goes to 0. There's electromagnetic optics, where we flick the electric field somehow, and we have these disturbances which propagate out at the speed of light. Electromagnetic radiation is what light actually is. It's the most general classical theory. Finally, to explain the real deep nature of light, we have to move to quantum optics. And for our purposes for this course, we're just going to take the fact that there are photons that travel at the speed of light. They have energy h bar omega and momentum h bar k. And now we've really looked at the full picture of optics as it propagates in free space. Next week, we're going to look at what happens when it hits atoms, when it hits matter. We're going to look at the interaction of light with matter, starting with a macroscopic picture, then looking at individual atoms, and we're going to be able to derive things like Snell's law and the law of reflection, and predict how much light is going to bounce back when we shine this laser pointer on a piece of glass. All right, and we'll see you next time for that. Thanks.